We're going to get into acid-base equilibrium here now on 10.4. With equilibrium, of course, we have these reversible reactions. And so we have reactions that go forward and backwards. We can cause shifts in how quickly it goes forward and backwards according to something called Le Chatelier's principle. So you have two reactions taking place, and in your reversible reaction, the reactants and products are switched, and so the reactants become the products in the reverse, the products become the reactants. Of course, we usually don't write it as two separate equations, but instead as one equation with the forward and reverse reaction arrows like that. And initially what happens is you're going to start out with all your initial reactants, the forward reaction reactants, and so you'll have some amount of those, but as they react, you're going to produce products, and so the reactants are going to get used up somewhat, and they're going to decrease while the products are increasing. Well, what happens then is eventually we get to a point where the rates of the two reactions are equal, and so as reactants form products, those products are reacting away to form reactants, and the amount of each of them stays the same over time, and so we've established what's called equilibrium. However, we can cause that equilibrium to shift and change where these plateaus are based off of changes that we can make to the reaction itself. Anyway, we're going to look at how these things work at different stages in equilibrium. Before equilibrium is reached, the concentration of the reactants and products are not equal. I suppose I should have done one or the other and not the not equal sign. There we go. Initially, the reactants have a rate of reaction that is faster. They're getting used up faster than the products are being used up. At equilibrium, the two are equal, and at equilibrium, the concentrations do not change. Which actual particles make up the reactants and products, those are going to change, but because the rate of formation of each of them is equal at equilibrium, then the total quantity or concentration is not going to change unless we do something to cause a shift to that. In Le Chatelier's principle, we can shift it by placing a stress on there. And the stress is usually changing the outside conditions or adding or removing chemical to the reaction itself. And so the analogy here is that we have two tanks that are connected and the water level will reach equilibrium. Well, if later on we add water to A, now the two are not equal. And so we're going to have the rate of the forward reaction, if you will, here. The water flowing out of tank A into tank B is going to increase. And it will keep going there until there is a new equilibrium. Now, where the analogy doesn't work perfectly is once they're in the two tanks, there will be some random particle motion, but you're not going to have many particles from tank B ending up over in tank A. With a reversible reaction, that can and does happen, but at the new equilibrium, notice we have a different level, but once again, the concentrations of the two are equal. So if we have this reaction here and we add more HF, well, we now have more reactant, which means that reactant is going to collide with the other reactant more frequently, according to collision theory, which you should have got back when covering reactions. And so then because they collide more frequently, it's going to cause the rate of the forward reaction to increase, and we're going to end up with a new equilibrium after that. If instead we take out the HF, then those collisions are less common, and these collisions now kind of have more space, but they will shift to relieve that stress on the system, and they will replace the HF. And so adding a reactant shifts it to the right, removing a reactant shifts it to the left. They're opposite. And to be honest, I think through it every time I do this. I don't memorize those properties. Imagine it's a seesaw and that we're trying to get it to be even. And so if we remove weight from this side, well, then we're going to have to move weight from the other side over here to this side to get it to where it's equal again. And so that's how I think of it, and I think through it like that every time. I genuinely do not have these memorized. Anyway, if we get into manipulating the product side, if we add fluoride ion, then again, these collisions are going to be more frequent. It's going to increase the rate of the reverse reaction. If we were to remove fluoride ion, which it doesn't have here as an example, or manipulate the other two in here, the water and the hydronium, but if we removed it, then we'd shift it to the right. Anyway, here are all four of those: adding and removing reactants, adding and removing products, what change it does and what direction it shifts. I've been saying left and right here, but shift in the direction of the reactants and products works as well. As a side note with that, we are referring to the forward reaction of reactants and products. The reverse reaction, you could switch the label. I will usually myself say the forward reaction reactants to forward reaction products. But if you're not going to specify, it's assumed it's the forward reaction. Pause or rewind and pause if you want to take a look at that. In terms of health, since the goal is to get into life processes here, hypoxia, having too little oxygen in your bloodstream happens. And so when the O2 level is high, we have no problem forming hemoglobin that has the oxygen bonded to it, which is then what's in your bloodstream and transports oxygens to your cells. As the initial slide that I just skipped over here showed, it was talking about mountain climbers. When you get up there, the amount of oxygen gas that's available is less, and so the reversible reaction shifts to the other side, and your body does not have as much oxygen dissolved in the blood there, or aqueous here, bonded to the hemoglobin to transport to the cells. And so hypoxia is not having enough oxygen. In fact, hypo is low. Oxy, you can see here the oxygen, so low oxygen, and it can cause you to black out and too long. You can even die from not having enough oxygen, of course. And so this here just goes through those details, but by removing the oxygen, we have a shift to the left. We increase the rate of the reverse reaction, and the amount of product goes down, and your body needs that product. You can read the details there or in your textbook. Anyway, we're going to look at the example here and decide whether it favors the reactants or products. So first, if we add some H2CO3, that's going to shift it in the direction of the products. If we remove some HCO3 minus there, that is also going to cause a shift towards the products because we're going to be trying to restore balance on both of those. If we add H3O plus, then on this one, if we're increasing that, then this one here is going to favor the reactant side of the reaction and will cause a shift to the left.